Good morning, everyone. So, in the last class, we have seen the application of irreversible thermodynamics to quantify the solvent flux during the reverse osmosis process. So, we started with the basic equations and kept on deriving things, depending on several assumptions and and simplifications, and ultimately we arrived at the osmotic pressure model for quantification of the solvent flux through the porous membrane. Now, in today's class, we will derive the leftover portion of it, that is what is the solute flux through the porous membrane. So, let us develop the solute flux through the porous membrane. Again, the assumptions involved are: one is steady state, second one is one dimensional flow field that we will be talking about, and third one will be no coupling. Okay. So, we integrate the solute balance equation at the steady state. So, N1 0 to L, L is the thickness of the membrane, minus L11 integral C1m prime to C1m double prime del mu 1 del C1m d C1m at constant pressure temperature plus P2 to P1 del mu 1 del P dP. So, if we now we will substitute, we will invoke the definition of partial molar volume and put it here. So, we will be getting minus L11 C1m prime to C1m double prime del mu 1 del C1m d C1m plus V1 bar L11 delta P. Delta P is the pressure drop across the membrane, and for the dilute solution we know the activity will be almost equal to concentration. So, we will be utilizing the concept of dilute solution. For dilute solution, our activity will be almost equal to concentration, and let us look into the expression of chemical potential. Mu is equal to mu naught plus RT ln A1m. So, that will be in the dilute limit, it will be mu 0 plus RT ln C1m. Now, let us look into the derivative del mu 1 del C1m. It will be nothing but RT del ln C1m by del C1m. Okay. So, just we are putting the mu 1 0. Okay. Now, you can combine the equation with the integrated form, and this becomes L11 RT ln C1m prime C1m double prime plus V1 bar L11 delta P. So, the expression of solute flux, this is a molar flux, this becomes L11 RT by length, thickness of the membrane C1m prime C1m double prime plus V1 bar L11 divided by L delta P. Now, again there are certain approximation one can have. In most of the cases, the second term of this expression becomes pretty small. So, generally the second term V1 bar L11 divided by L times del P are negligibly small compared to this term. So, therefore, we can get an expression of solute flux as L11 RT over L ln C1m prime divided by C1m double prime. So, this gives a logarithmic distribution of the solute in the downstream and the upstream of the membrane surface. Okay. Now, again since we are already assuming a dilute solution, it is well known that the coefficient L11 will be roughly proportional to d1m multiplied by C1m. This is for dilute solution. D1m is the solute diffusivity through the polymeric membrane phase, and C1m is the concentration of the membrane. Now, if you put that expression here, the final expression of N1 becomes L11. We will just start it couple of steps earlier, del C1m gradient of C1m, and now we will put L11 as minus D1m C1m del mu1 del C1m. This is dC1m by dx. So, if you integrate this equation out and del, you just put the expression of del mu1 del C1, okay, you put the expression of del mu1 del C1 m from the earlier derivation and integrate it out, it will give you the expression of solute flux as d1m RT divided by L C1m prime minus C1m double prime. Now, if d1m is treated as constant, membrane thickness is constant, R is universal gas constant, T is the temperature. For isothermal case, for isothermal transport, N1 the solute flux becomes some constant multiplied by C1m prime minus C1m double prime. This is known as the solute permeability through the membrane. Now, this solute permeability will be related to the solute flux. This is a solute molar flux. Okay, this is a molar flux. This molar flux of the solute will be related to the molar flux of the solvent, and we will be coming to that, but this relationship is known as the solution diffusion model. So, for the solvent flux we had the osmotic pressure relationship or Darcy's law. For the solute flux to the porous membrane, we have derived the solution diffusion model. What solution diffusion model presents? It presents a relationship of solute flux through the porous membrane with respect to its concentration in the upstream side and in the downstream side in the membrane phase. Okay. Now, this solute flux is related to solvent flux. Through the membrane. Now, if you look into the expression of the solvent flux, it has a unit of molar unit, moles per meter square per unit time. So, volumetric flux J becomes N2 times molecular weight of the solute multiplied by 10 to the power minus 3 divided by rho of solution, okay, that gives you the unit of meter cube per meter square second. So, that is the relationship of molar flux to the volumetric flux. J is having a unit meter cube per meter square second, and N2 is having a unit moles per meter square per unit time. Now, so what is solute flux? Solute flux is nothing but J times C1m double prime, right. So, that is the concentration of solute in the permeate. This is a solvent flux multiplied by the concentration of the solute, that will give you the solute flux, moles of solute per unit meter square per meter square per unit time. Now, therefore, the solution diffusion model can be written as J C1m double prime a constant Ks multiplied by C1m prime minus C1m double prime. Okay. So, this is the relationship of the solution diffusion model and solvent flux. Okay. Now, if you can now in fact this constant Ks will be having a different unit compared to the constant that appeared in the solution diffusion model, because of the volumetric flux that we are talking about. Okay. Now, J will be let us say if you write down the expression of observed retention is 1 minus concentration of solute in the permeate divided by concentration of solute in the feed, that means C1m double prime divided by C1m prime. Now, when you are writing this expression, that means you are assuming that the concentration of solute on the membrane surface is same as the bulk concentration. That means we are not considering the in absence of concentration polarization or a mass transfer boundary layer on the feed side. If that is not present, then whatever the concentration is in the bulk, that will be same as on the membrane surface. That can be realized if and only if you can have a very high stirring in the feed side. If you have a very high stirring in the feed side, there is no polarization of the solute on the feed side. Whatever the concentration appears on the membrane surface, that will be appear on the bulk. But in an actual case, it is not happening. You have to couple this equation with the concentration polarization model, that we will see later on. So, if you write down this expression, if you just eliminate this concentration in favor of the observed retention, the expression of J turns out to be some constant divided by 1 minus multiplied by 1 minus R naught minus 1, and we know the expression of J or the solvent flux from the osmotic pressure model, that is nothing but J is equal to Lp into delta P minus delta pi, right. We just derived this relationship. So, utilizing this relationship and the earlier one can write the expression of R naught as Lp delta P minus delta pi divided by Lp delta P minus delta pi plus B. What is B? B is nothing but it is equivalent to Ks, okay, equivalent to Ks, and this is the solute permeability in the membrane phase. Now, let us look into the implication of variation of observed retention, how it varies as an operating condition, which is the most critical in the case of reverse osmosis, that is delta P. If you increase delta P, if we increase the delta P, what happens? The B becomes very insignificant, and you will be getting R naught tends to 1. Okay. So, that means for higher pressure, if you plot observed retention versus delta P, in case of reverse osmosis, you are going to expect a curve something like this, and this value will be equal to close to 1. Okay. On the other hand, in case of ultrafiltration, so this is the case of reverse osmosis and nanofiltration membrane. That means observed retention increases as you increase the operating pressure drop. In case of ultrafiltration and microfiltration, the case is simply reverse, because your pore size is very high, the more solutes will be permeating through the membrane. In that case, observed retention will be going down as you increase the pressure. In case of ultrafiltration and microfiltration, the trend will be just reverse. Now, physically what it means? Physically it means that the membrane becomes non-porous. It has a certain capability to retain the solute. So, the solute will be retained to that maximum possible extent, but if you increase pressure, the solvent being smaller in size, more solvent will be permeating through the membrane. So, therefore, since the extent of retention by this reverse osmosis or nanofiltration membrane is almost constant, the concentration of permeate of the solute in the permeate stream will be more or less constant. because it has a particular capability, it cannot retain beyond a particular point. So, the concentration, so you cannot, by changing the operating pressure or any operating conditions, it is very difficult to increase or decrease that capacity. Okay. So, the concentration of the solute in the permeate stream will be more or less constant, but if you still increase the operating pressure, more solvent will be coming through the membrane. So, therefore, the permeate stream will be diluted. The concentration of solute in the permeate will be less, because the total amount will be same, you are adding more water to it. So, it will be diluted. So, therefore, observed retention will be tending to 1. So, physical significance is that more solvent permeates and making the permeate dilute. So, one can expect an increase in retention in case of reverse osmosis or nanofiltration as you increase the operating pressure drop. Okay. Now, there is another variation of solution diffusion model is solution diffusion imperfection model. What is this model? If you remember, in the derivation of solution diffusion model, we omitted one term, that is the delta P term, the pressure drop term. We have a term of, let us say, Ks times C1m double prime, C1m prime minus C1m double prime, plus another term, that is some constant, let us say K prime times delta P. What we said, generally these terms becomes very small. What is this term? This term signifies a diffusive term, because this is driven by the concentration difference. So, this is a diffusive term. What is this term? This term is a convective term, because it depends on the delta P. So, this is a convective term. For a pure reverse osmosis or nanofiltration membrane, this diffusive term will be dominant, because we are talking about non-porous, almost non-porous membrane. Membranes with small pore size, this is term 1, this is term 2, term 1 will be much greater than term 2. So, we can neglect the convective term. Okay, that we really did, but in some cases when you will be having some, because you know in a membrane there is no fixed pore size, you do not have or you cannot have a membrane of uniform pore size, there will be a distribution of the pore size in the membrane. So, there will be some pores which will be larger in size, some pores which will be smaller in size, and there will be distribution existing in the system, and you can find out the average distribution or average pore size. So, there may be some pores where the pores are larger, where the convective term of the solute flux becomes predominant. In that case, this term will be considered. So, it is termed as the imperfection to the membrane, because for a reverse osmosis or nanofiltration membrane, we are assumed to have we are supposed to have small pore sizes, because if there are some pore sizes there, because of the problems in casting or operating conditions in the casting, that is basically nothing but an imperfection to the membrane casting. So, this is known as the solution diffusion imperfection model. In this case, this particular term will be included. Okay. Now, what this means is that when you keep on increasing the terms like this, what you do, you really do not know how to get this value, how to get this value. Now, these are the parameters of the model. So, what you are going to do? You are basically do some calculations using an assumed values of these parameters, okay, and get the value of the permeate concentration and the permeate flux, and measure and compare these values with the experimentally measured values of the permeate concentration and permeate flux. Okay. Likewise, if the and see the difference. error involved in it. If error is large, then you have another guess set of these parameters. Okay. Likewise, you can keep on iterating and doing an optimization study. You can fix you can convert set of values of parameters. But the thing is, when you keep on increasing the complications in your model, the number of parameters will be increasing in your system. And if a system will be having a large number of undetermined coefficients, the less flexible the system is. So, it is always undesirable to have a large number of adjustable parameter in your system. Okay. So, that is this parameter becomes physically consistent, that there may be imperfection in the matrix. So, this pressure driven term there, but it includes another complication in the calculation as far as this calculation is concerned. This is physically more robust, but as far as the calculation is concerned, this becomes very weak because the number of adjustable parameter is increasing. Okay. So, you have to keep all these things in your mind during your calculations and modeling of the system. Okay. Then we look into the two terms, concentration polarization and membrane fouling. Okay. Before going into the concentration polarization membrane fouling, I would just like to elaborate one thing, that whenever we are talking about the calculation or the prediction of the permeate flux and permeate concentration, you have to understand that there are two distinct regimes in the transport. What are the two distinct regimes? One is the transport through the porous membrane, another is the flow outside the membrane in the flow channel. So, this is the flow in the channel and this is the flow through porous membrane. Now, how you will be modeling the flow outside in the flow channel? You will be doing a fluid dynamic study. You write down the equation of continuity, you have to write down the species balance equation, solute balance equation. So, you will be getting the and after solving that, C you will be getting as a function of x and y. Okay. And that has to be, so there will be a transport phenomena outside the flow outside the membrane, and there will be a transport phenomena inside the porous medium. Now, what will be the solute flux, and this will be coupled, these two will be coupled at the interface. Okay. Then combining these two transport, you will be getting the full prediction of the system. Okay. Now, whatever we have seen till now, so the flow through the porous membrane. So, we have got the solution diffusion model to quantify the solvent flux. We got the we got the solution diffusion model to quantify the solute flux, and we got the Darcy's law or osmotic pressure model to quantify the solvent flux through the porous medium. Now, that has to be hooked up with the transport phenomena that is occurring outside the membrane in the flow channel. Now, this is very complicated. Flow through the porous medium is very complicated. The most simple version, the simplest version I just presented in the form of Darcy's law and the solution diffusion model. If you remember what it does, what it gives, solution diffusion model, it says that permeate flux, volumetric permeate flux or solvent flux is nothing but B times C1 m double prime, C1 m prime minus C1 m double prime divided by C1 m double prime. Now, actually this will be B times C1 m Cm minus Cp divided by Cp. Cm is the concentration of the solute in the concentration solution in the membrane feed interface, and C1 m double prime is nothing but permeate concentration, right. Now, this gives a relationship between a functional relationship between Cm and Cp. What is Cp? Solute concentration in the permeate, and Cm is the solute concentration in the feed membrane interface. This gives a relationship between that. And if you remember, the real retention, the definition of real retention is 1 minus Cp by Cm. and what is Cp? Cp is simply Cm into 1 minus Rr. So, this also gives a relationship between Cp and Cm. This is a different relationship. So, what is the difference between the two? If you talk about the real retention, then we cannot talk about the solution diffusion model. They are mutually exclusive. Both are almost equal to same, because real retention is nothing but, as I discussed earlier, it is nothing but a partition coefficient of the solute in the permeate phase and in the feed phase. On the other hand, solution diffusion model becomes, so what is real retention? Real retention is basically a parameter which dumps all the flow characteristics of the solute through the porous membrane. So, this is one adjustable parameter. This is not an adjustable parameter. We have discussed in earlier classes how to determine it experimentally from a different set of experiment. You conduct the experiment at high turbulence, so that observed retention will become almost a real retention. On the other hand, experimental determination of this coefficient B will be extremely difficult. It is almost impossible. So, it has to be it has to be determined again against the experimental values, okay, by doing an optimization study. Okay, the method I just discussed, you have to have a guess value of B and then predict the permeate concentration, permeate flux, and compare with the experimental results and do an optimization study. So, therefore, sometimes this formulation becomes very handy, because real retention can be experimentally determined separately and can be incorporated in a model. So, the whole model can run in a predictive mode. On the other hand, if you adopt a solution diffusion model to quantify the solute flux to the membrane surface through the porous membrane, you do not know the value of B. In that case, what you have to do, in order to determine the value of B, the method I just mentioned, you have to use the experimental value. So, the modeling cannot be in predictive mode if you use the solution diffusion model. What you can do maximum, suppose you can have 20 experiments or 27 experiments, you can take half of the experimental setups using different operating conditions and use those experimental values data to optimize the value of B. Once you optimize this value of B, then for the rest of the data you can run it in a predictive mode. So, in that case, solution diffusion, the shortcoming, the advantage of solution diffusion model is it is physically more correct compared to the real retention formulation. On the other hand, it creates a complication or an inaccuracy during the experimental modeling or calculation stage, because for the half of the you have to use the experimental values to determine the value of B. On the other hand, you can use the real retention formulation for a completely predictive calculations. Okay, that is the difference between the solution diffusion model and the real retention formulation. Now, let us come to the concept of concentration polarization. Now, suppose this is a membrane system and you are having a feed at a concentration C naught, and you have conducted an experiment and getting a concentration in the permeate as Cp, okay, permeate concentration. Now, it is not that simple that you are going to get a concentration C naught in the feed stream and going to get a permeate concentration Cp. There is something there is a deposition of solutes on the membrane surface which provides a concentration boundary layer in the membrane surface, okay, that we have discussed in the earlier lectures. Now, this concentration becomes Cm. So, the membrane, as far as the membrane is concerned, the membrane does not realize or does not experience or does not recognize the presence of the bulk concentration. Membrane experiences only the surface concentration over it and a permeate concentration on the downstream. So, there will be accumulation of solutes over the membrane surface. This is known as concentration polarization. That is polarization of the solute particles over the membrane surface. Now, there are several implications of this concentration polarization. First one is more concentration polarization means more solutes will be deposited over the membrane surface. Why there will be solute concentration on the membrane surface? Because this is a pressurized system as you remember, in case of reverse osmosis, we are talking about pressure of 25 atmosphere. In case of nanofiltration, we are talking about pressure about 15 atmosphere, ultrafiltration 6 atmosphere, microfiltration 2 atmosphere. So, it is a pressurized system. So, because of the convection, more solutes will be coming and depositing over the membrane surface. So, concentration polarization is more, that means membrane surface concentration is more. So, if membrane surface concentration is more, then osmotic pressure across the membrane will be more, because osmotic pressure is an increasing function of concentration, and that we have discussed earlier. So, concentration polarization high means your osmotic pressure at the membrane surface will be high. If the osmotic pressure at the membrane surface will be high, in order to get a higher flux, your operating pressure has to be more. Okay? So, if osmotic pressure is high, then it gives a reduction of driving force. Delta P minus delta pi. So, if delta pi will be, if delta P is same, delta pi will be more, and there will be a reduction in the driving force. There may be formation of gel layer over the membrane surface. What is formation of gel layer? So, basically, if in an actual system, the membrane channel will be long in the tune of 1 meter, 2 meter, like that. 1 meter means 3 feet. Okay, it may be several meters. Now, initially, that we have discussed earlier, that at the entrance of the channel, the concentration polarization will be less, the concentration boundary thickness will be less, and it will be increasing slowly over the channel length. And this growth of concentration boundary layer will be extremely slow, because the entrance length will be pretty high in case of the solutes like this that we have discussed. The entrance length required will be 0.05 into Reynolds number into Schmidt number, and we are talking about a solute of very low diffusivity, that means very high Schmidt number. So, therefore, the entrance length will be extremely high. So, therefore, as you go down in the membrane channel, the surface concentration will keep on increasing. The surface concentration will keep on increasing, and beyond a particular point, it may exceed the solubility limit of the solute in that particular solvent at that particular temperature. So, what happens at that point? If it exceeds the solubility limit, the whole solute will be precipitated over the membrane surface as a solid. In that case, it is termed that it forms a gel. Some cases like polymers, proteins, gel is not that distinct. In that case, gel will be basically very highly viscous thick solution. So, what formation of gel gives? It gives an extra resistance against the gel, means it is a very thick, its viscosity will be extremely high. So, the porosity will be extremely low. So, it acts as a dynamic membrane, an additional membrane in presence of the actual membrane, the physical membrane. So, it is called a formation of a dynamic membrane. So, therefore, it offers an extra resistance. So, formation of gel layer means extra resistance against the solvent flux. So, therefore, the operator should be very careful that gel formation, he should operate under the conditions such that gel formation is avoided. Okay. Now, for some solutes, gel formation is inevitable. For example, solutes like pectin. Pectin is a well known gel forming agent, PVA, polyvinyl alcohol. This is a polymer, this is a polysaccharide. Okay, this pectin is a polysaccharide, and it is it occurs in high quantity in the fruit juice, in citrus fruit juice. So, these are all gel forming agent. These are well known gelling agent. For filtration of such gelling agents, gel formation is there, it is unavoidable, and it occurs from the very beginning of the operation. Okay. Third implication of concentration polarization is that increase in solution viscosity, near membrane feed interface. Okay. So, it becomes concentration increases, and what are the various parameters, kinetic parameters, transport coefficients involved in the solute balance equation. The transport coefficients, those are involved in the solute balance equation. One is viscosity, another is diffusivity, another is density. Now, we know that viscosity, diffusivity, density, all the three parameters are functions of concentration. Now, out of these three parameters, viscosity is the strongest function of concentration and diffusivity and density are the weaker functions, because between diffusivity and density, density is the weakest function of concentration. So, once for the high concentration polarization, membrane surface concentration increases, means your viscosity increases very high. That means viscous solution is there present near the membrane surface, again it offers an extra resistance against the solvent flux. Okay. The fourth implication is that increase in concentration polarization means your membrane surface concentration increases. So, therefore, the concentration difference across the membrane will be more. If concentration difference across the membrane will be more solutes will be trying to get transported through the membrane. So, there will be chance, high probability of pore blocking. Okay. So, more solutes will be transported through the membrane, and since the pores are not always straight cylindrical pores, they are all interconnected zigzag pores. Some of the pores may be blocked, some of the pores may be completely blocked, some of the pores may be partially blocked, partial clogging, and all those things can occur. Okay. So, this pore blocking, what it does? This pore blocking will reduce the permeability of the membrane. Now, let us look into the implication of these four phenomena. First one, increase in osmotic pressure. Increase in osmotic pressure means your driving force will be less. If the driving force will be less, the productivity of the process will be less, the solvent flux will be less. That means your productivity of the process will be less. Formation of gel layer over the membrane surface, it offers an extra resistance against the solvent flux. So, therefore, solvent flux will be decreasing, permeate flux will be decreasing. Third one is increase in the viscosity of the solution. If the solution viscosity increases, it offers again an extra resistance against solvent flux. So, solvent flux will decrease. Fourth one is pore blocking, it reduces the membrane permeability, LP will be decreasing. If LP decreases, again the solvent flux will decrease. So, all these four phenomena will point to the common result, that is the decrease in the solvent in the permeate flux. Solvent flux in the permeate stream, decrease in permeate flux. That means it decrease in productivity of the process. This phenomena is known as flux decline. In an actual process, because of this phenomena, now all these phenomena can occur one at a time or more than one at a time or all of them at a time. Now, because of that, the flux will decline over the period of time, and this is known as the flux decline phenomena in the membrane process. Now, there are considerable research going on nowadays to avoid minimize the flux decline. Now, this concentration polarization cannot be avoided, it is always there, but it can be minimized, and there are several techniques there for minimizing this concentration polarization, and we will be looking into some techniques later on in our course. Okay. Okay. Now, let us look into the fouling. Fouling of membrane. Now, membrane fouling is related to concentration polarization. You must be realizing now, related to concentration polarization. depending on the ease of removal of fouling, the fouling can be categorized into two types. One is reversible fouling, another is irreversible fouling. What is reversible fouling? In case of reversible fouling, the deposition over the membrane surface. For example, the formation of boundary layer, concentration boundary layer, formation of gel layer, formation of a very thick high viscous solution over the membrane surface. If the flux decline occurs because of this, now if you stop the operation and open up the system and wash the membrane, all these depositions will be washed away. If you rinse the membrane or if you use an appropriate washing protocol, all of this will be removed. So, you get back your original permeability of the membrane. So, these are known as the reversible fouling. So, fouling can be reversed, you can get back the original permeability of the membrane. On the other hand, now pore blocking or solute adsorption inside the pore now some of these things, most of these cases, pore clogging etc., you cannot get back the original permeability of the membrane. So, this loss of permeability in this case becomes irreversible. So, you cannot get back the original permeability of the membrane, some of the permeability is always lost. So, this is known as the irreversible fouling. So, irreversible fouling generally occurs because of the pore blocking or pore clogging, partial or complete, or adsorption of the solutes inside the pores. And reversible fouling they occur because if there is a formation of a concentrated solute layer over the membrane surface. Reversible fouling can be the foulant layer can be removed by adopting a suitable washing protocols, or in the case of irreversible fouling, some amount of permeability of the membrane is irreparably lost. Now, let us look into the modeling aspects. In fact, we have derived the simplest model earlier. Modeling means prediction of system performance prediction. Okay. What is performance prediction? Prediction calculation of, given the operating condition, geometry etc., you should know what is the value of permeate flux. What is permeate flux? This is nothing but the productivity of the process and permeate concentration. The simplest model, we just think about a one dimensional steady state model, that is known as the film theory, that we have discussed and derived earlier, probably a couple of classes back, and I will just give the highlight of this. There are several assumptions in the film theory. It is assumed that the solute layer, forms a concentration boundary layer over the membrane surface of constant thickness. So, that obviously that assumption is not very correct, because most of the channel near the entrance there will be an entry length existing where the thickness is growing, but it is not constant. Number one. Number two is that in this case we have assumed that there will be a convective flux towards the solute existing. This is by the delta P JCP JC, and there will be a diffusive flux away from the membrane surface because of the concentration gradient. Membrane surface concentration is more compared to the bulk concentration. So, there will be diffusive flux because of the concentration difference, Fick's law, and there will be convective flux away from the membrane surface at the steady state J times Cp. Now, at the steady state, all the summation of all the fluxes will be equal to 0, and you will be getting a differential equation. By solving that, you will be getting the expression of film theory that we have already derived earlier. the expression of film theory is J is equal to K ln Cm minus Cp divided by C naught minus Cp. That we have already derived earlier, I am not deriving it once again. What is K? K is the mass transfer coefficient. Now, mass transfer coefficient is very important parameter in this case, and it can be obtained from the Solute number relations. In fact, we have touched upon some of the Solute number relations. For flow through a tube, okay, the tube geometry will be something like this. The fluid is flowing across a tube, and inner surface of the tube will be wrapped by a membrane. Okay. So, membrane surface area will be pi dl. On the other hand, if it is a flat geometry, that means if there is a channel like this, and if you put a membrane on the on the bottom surface and the top surface, the membrane area will be length times width, okay, twice of that. One surface will be available at the bottom, one surface will be available at the top. That is for the flow through a rectangular channel. For the flow through a tube, the Solute number relationship will be K d by d 1.62 Reynolds Smith d by L raised to the power 1 upon 3 for laminar flow. Laminar flow means Reynolds number less than 2200. For rectangular geometry, Solute equal to K d by d equal to 1.85 Reynolds Smith d by L raised to the power 1 upon 3. D is the equivalent diameter, and it will be equal to 4 into half height of the channel that we have derived in the earlier classes. D is the diffusivity of the solutes, and this D is the diameter of the tube, and the equivalent diameter, Reynolds, Smith, etc. can be obtained from the flow conditions and the properties and the geometry. Okay. Now, one can calculate the mass transfer coefficient using these relations. In fact, these are relations and they are not correlations, and in fact, one of the earlier classes we discussed about the difference between the correlation and relation. These relations are theoretically obtained from the very first principles. On the other hand, in most of the industrial scale applications, the flow conditions are not laminar, they are turbulent. Okay. For turbulent flow, that means your Reynolds number greater than 4000, we can use the Dietz-Bolte relationship K d by d or K d e by d. This will be in case of tube, and this will be in case of rectangular geometry. This will be nothing but 0.023 Reynolds raised to the power 0.8 Smith raised to the power 0.33. Okay. So, this Reynolds number will be based on diameter if it is a flow through a tube, and it is based on equivalent diameter if it is flow through a rectangular channel. Now, this is a correlation. This is if you remember Dietz-Bolte relationship for the heat transfer case. This is indeed a correlation, and from the heat and mass transfer analogy, there are similar non-dimensional term, Nusselt number for the heat transfer, Solute number for the mass transfer, Smith number for the mass transfer, Prandtl number for the heat transfer. So, therefore, from the heat and mass transfer analogy, we use the Dietz-Bolte correlation to calculate the mass transfer coefficient. If you have now in some industrial application, there are stirred cells. So, basically this is a big vessel. In the big vessel, if you have a very important item which will be the feed is very small and very costly, then you can use that stirred cell. So, there is a flange there, you put the membrane in the bottom of the cell and you put a stirrer there, seal the top, and there will be a tap which will be pressurized from the outside by using nitrogen cylinder or something like that. So, this is called a stirred cell. In stirred cell, the mass transfer coefficient of Solute number correlation is obtained as is given as Kr by d is equal to 0.285 Reynolds raised to the power 0.55 Schmidt raised to the power 0.33. Okay. So, R is basically the inner diameter of cylindrical cell, okay, star cell, and Reynolds number is defined as rho omega r, that is the linear velocity multiplied by the r divided by mu. So, rho omega r square by mu. Okay. What is omega? Omega basically starer speed in radian per second. So, this is not RPM. RPM can be converted to radian per second, and all of you know about it. And Schmidt number is basically mu by rho d. And this is for Reynolds number less than 32,000. This relationship is valid for Reynolds number less than 32,000. In fact, this is a correlation. For if the Reynolds number is greater than 32,000, another correlation is available. For Reynolds number greater than 32,000, you have Sherwood equal to K R by D is equal to 0.0443, Reynolds raised to the power 0.8, Schmidt raised to the power 0.33. Now, for Reynolds number greater than 32,000, you can use this correlation for estimation of mass transfer coefficient. So, we can use several appropriate mass transfer coefficient relationship under the laminar flow conditions, under the turbulent flow conditions, depending on the geometry. Okay. And using those mass transfer coefficient, one can have a you can calculate you can have a system prediction. But how to do that? That we will see in detail in the next class, in tomorrow's class. Okay.